of the hour. We're a little over the top of the hour. That's okay. So hello, everyone, and welcome to the November NASA Night Sky Network member webinar. We are hosting tonight's webinar from the Astronomical Society of the Pacific in San Francisco, California. And we are very excited to welcome our guest speaker, Dr. Travis Fischer from the Space Science Telescope Institute. But before we get a little further into our introductions, here is Vivian White with some announcements.
Hey, all right. It's great to see everyone out there. Such a good crew tonight. We have a lot of you, and I am thrilled to announce that the pins have arrived, and this is all Kat. As many of you know, Kat's just joined the team this year, and she is earning her keep. Check out. Do you want to show them the pins?
I do. So we did something a little bit different with the pins this year. I know traditionally we have our two astronomers that point up at the object in the night sky. But, and let me know if you all can see this, this is going to be our annular and total solar eclipse pin for 2023 to celebrate everyone that has participated and had events this year. So make sure you tell your coordinators, if you are not a coordinator yourself, or if you are a coordinator, make sure you tell everyone to go ahead and fill out that form so that you all can get your pins this year.
Awesome. I'm just adding some links to the chat. If your club is active in the Night Sky Network, that is, you have reported on 5 events in the last year or 2 in the last quarter, that qualifies you to receive 3 free pins. And you can also order more if you want for just the price of shipping, basically. And if you're not active, it's really easy to get active. I'm just adding these to the chat here. And as a bonus, if you post 10 upcoming events for 2024 on the 2024 calendar, we will go ahead and send you some extra classes this year. Look out. Is there a feedback somewhere? Sorry, I've got something going on.
I hear you now. You're fine.
Great. Awesome. Great. So make sure to post your upcoming events on the NSN calendar. If you have any questions, I'll put a link in how to do that as well. Kat's got some office hours coming up on Tuesdays and Fridays. I'll put that link in the chat. And then for those of you who have not yet gotten the Eclipse ambassadors spiel, we are really excited. We have about 550 Eclipse ambassadors across the country. We're working on a couple hundred more. These are, you can be an ambassador in your community before you head out to see the eclipse. If you're going, we'd love to have you, and keep an eye out for the link to that. One more, Kat, is you, I think?
Yes. So NASA is looking for folks that will help them live stream the eclipse for April 8th. And if you happen to live in any of these 4 regions that I'm about to paste in the chat, Dallas, Texas, Indianapolis, Indiana, Niagara Falls, New York, and Holton, Maine, we would love it if you applied to be a live streamer and to contribute to the broadcast. You can go ahead and fill out the form, and it'll ask you some questions about what kind of equipment you have, if you're interested, and do you have a white light filter? Do you have a hydrogen alpha? Do you have a calcium filter? If you are in this area or you're willing to go to this area, then please go ahead and fill out the form, and they'll get in touch with you, and then I'm on those emails as well, and we'll coordinate so that we can broadcast the eclipse to everyone globally April 8th.
Awesome. Great.
All right.
Okay.
All right. So without further ado, let's go ahead and get back into it. This is the November NASA Night Sky Network webinar. And as always, you can send an email to us anytime at nightskyinfo@astrosociety.org. And if you have any questions for our guest speaker, please submit them into the Q&A window and not the chat window, so that we make sure that we see your questions and they don't get lost in the standard chat. This evening, NASA Night Sky Network welcomes Dr. Travis Fischer to our webinar on active galaxies, monsters of the deep space. Joining the Space Science Telescope Institute in 2020 as an ESA Aura astronomer, Dr. Travis Fischer provides support for the Cosmic Origins Spectrograph aboard the Hubble Space Telescope and acts as a lead for communications and testing on the Hubble Advanced Spectral Product, or HASP program. He previously served as a research facility through both George Mason University and the United States Naval Observatory and the Catholic University of America at NASA Goddard Space Flight Center. Before this, he was a James Webb Space Telescope NASA postdoctoral program fellow, and he continues to pursue an active research career studying active galactic nuclei, their influence on host galaxies they reside in, and analyzing the integral field unit. Please welcome Dr. Travis Fischer.
Wow. Thank you so much, Kat. Wow, what a wonderful introduction. All right. Hey, everybody. I'm going to share a screen here, and we're going to start a talk here. Where's the talk? There's the talk. Great. All right. So, yes, we're here today. We're going to be talking about active galaxies, monsters of the deep, space. And so I'm not really sure what the level of comfortability is with active galaxies, what exactly they are. So we're just going to start basic level here and this about what are galaxies, right? Very simple start off point here. So galaxies are clusters of stars, billions and billions of stars that are held together by gravity. All right. So we do have these active supermassive black holes or quiescent supermassive black holes in the centers of them, but that's not what's binding them into these galaxies. It's the stars themselves that are spinning around and being bound by gravity. In between all of the stars is mostly space. These are nearby images of nearby galaxies, and we can see there's a lot of individual space between all these individual pixels of light that are stars here. And so we also live in a galaxy. Our solar system is in a galaxy. We call that galaxy the Milky Way. And so our galaxy looks a lot different from everybody else because we live in it. So that picture above on the top is the view that we see when we're looking at the night sky. Everybody, all the amateur astronomers, I'm sure are very familiar with that kind of view. And then on the bottom here is a top-down cartoon then of what we think the setup of the Milky Way galaxy looks like, down to the positions of the spiral arms that are within it. So the image that you see on the top then is not just a look forward into the center of the galaxy, but it's a 360 view. So we can kind of see that we can spin around and look in a 360 around the Milky Way galaxy, and that's what you're seeing across these images that are often on posters of the Milky Way galaxy that we live in. So in most, if not all galaxies, at the very center resides a supermassive black hole. Here's a picture of ours. This is Sagittarius A star. That's the name of the supermassive black hole inside our galaxy. And we're sure, yes, that pretty much every single one of the galaxies has one of these. And so what is a black hole? That's really the next question then, if we're moving from galaxies down to the active parts, that we're going to talk about the black holes then. So more importantly, what isn't a black hole? A black hole is not a wormhole. It's not a portal. It's not a time rift into another dimension. All right. It's not going to be any sort of tear in the fabric of space-time, at least in the sense when we're trying to understand physics and how the universe works. We do not understand it to be a tear in time. Instead, we say that a black hole is an object. Black holes are objects, just like anything that you would expect to observe in the rest of the universe, be it a planet or a satellite or a horse or a gallon of milk. Black holes are objects just like anything else that you're familiar with. And the only thing that's really different between a black hole and any other object is that they're extremely compact. And so what do I mean by this? So this is a star. This is a massive star, an A-type star. This is 8 times the mass of our sun. And when it reaches the end of its lifetime, it's going to explode. It's going to have a really bad day. And at the end, it's going to form a black hole. And this black hole, which has a similar mass to what it was before it exploded, is now about the size of Rhode Island. All right. The stellar mass black hole diameter for an 8-mass black hole progenitor is about 30 miles in diameter. So it's super small. On the other hand, we have the other flavor of black hole, and that's the supermassive black hole. And so in comparison, here is a scale representation of our sun, and then Sagittarius A star lurking behind it. And so while it is only 18 suns in diameter, the mass inside of Sagittarius A star is more than 4 million times that of the sun. So you can tell then that this must be a super compact object to only be an order of magnitude larger in diameter, but 6 orders of magnitude larger in mass. And then to bring that kind of back to where we just were, so there's Sagittarius A star, there's the sun. Here is going to be Earth, right down there, that pixel that flashed. And then you can imagine that the stellar mass black hole, that the black holes that exist more often inside of each galaxy, is still like a subpixel inside of that pixel. So the two sizes that we're used to between stellar mass black hole and supermassive black hole are very enormous in their depth of scale. So the next question is, are black holes dangerous? This is a question that I get as a black hole astronomer all the time. And so before I answer that, I posit these other questions, like, is swimming with a shark dangerous? Yes, we don't do that. That's a bad idea. Instead, what we do is we place ourselves in a cage far away and observe the shark safely, and then we have a good time. Likewise, when we're observing volcanoes, we do not sit on the volcano while it's erupting. You're going to have a bad time. You're going to die. However, if we do want to study a volcano while it's erupting, we place ourselves at a safe distance away from the volcano. We're able to observe what's happening and we are safe. And I think you can see where we're going with that. If we're trying to observe a black hole, we do not go in the black hole. You're going to have a horrible time. You're going to become a strand of spaghetti and you're going to die again. However, if we're here on Earth at a safe distance away from a black hole, there is no danger in studying that black hole, and we are going to be safe and sound, and nothing is going to happen to us. So then black holes don't suck. That's another point that we have to understand, is that people are worried that black holes are these vacuums that are going to pass by and they're going to suck us in, and then we're just going to disappear without even knowing it. But we need to remember that they are just objects, just like anything else. So here's a little mind experiment for us. If we took the solar system that we have, that there's Earth and the other 7 planets, and we took out the sun and we replaced it with a black hole of equal mass, all right? So the black hole is going to have the mass of 1 solar mass unit. Everything's going to be fine. Those planets are going to keep orbiting around that black hole as if nothing happened, okay? There's not going to be any sort of vacuum that is going to come with that black hole and pull us all in. It's all about gravity. However, I mean, we are losing the solar radiation and not being warmed by the sun, so all the planets will freeze, and then we will die that way. But that's a different problem for a different talk, so we don't have to worry about that. So how do black holes like work then when people say, Dr. Fischer, but like light can't even escape from a black hole? Like, how does that work? So this is the only equation I think I'm going to show tonight. And so this is just saying that the escape velocity off the surface of some structure, be it like Earth or a black hole, is approximately equal to the mass of the object you're trying to escape divided by the distance you are from the center of that object. So when you're trying to escape from Earth, you're going to use 1 Earth radius and you're going to use the mass of Earth. And that comes down to an escape velocity then of 11.2 kilometers per second. I don't really understand what that means with my American human brain. So I just say that's as fast as a rocket travels. It's actually a little bit faster than a rocket travels, right? Because a rocket's going to eventually come back. But it's approximately that fast, and you're able to leave the surface of the planet. However, if we replace Earth with a black hole, boom, and it's going to now have the same mass that we started with. It's 1 Earth mass. But now, if it's a black hole, the radius of that black hole is going to be about the size of a ping pong ball. So if you do the calculation again, then the escape velocity, if you use the mass of Earth and the distance is 1 ping pong ball, the required velocity to escape this black hole is 1 trillion kilometers per second. Again, unfathomable. I can't understand how fast that is, but we can put it in maybe the terms of the speed of light, and it has to be traveling over 3,000 times the speed of light. So that means that a photon, which travels the speed of light, the fastest thing that we know in the universe, still isn't traveling fast enough to escape the gravitational pull of a black hole. And that's why photons don't escape from a black hole either. So it's about gravity once again. So here is an idea of what happens then when we do have a collision course. Go animation, go animation. Oh, are you guys seeing that? Is it moving for you?
It's
The
not.
text is moving.
Oh man, hold
Oh,
on.
there we go.
I know there was another one. Okay, so it's okay. We're gonna be pressed for time anyways. But yeah. So when objects do come near a black hole, though, the gravity from that black hole is going to strip it and have that material swirl around that black hole. And if you rub your hands together, you're going to feel that friction between your hands gets nice and warm. And so what's happening here is a very similar effect where you have all of the dust and the material, the molecules from around that star that was stripped off are being pulled around that black hole and spinning at an incredible velocity. And it gives off tons of radiation, not just heat. It's going to give off ultraviolet and X-ray and gamma rays, tons of radiation. And when we have this event where we have a black hole accreting this material, eating this material and having it fall in, we call that an active galactic nucleus, or an AGN. And that's what we're going to be talking about tonight then, AGN activities. So when you have all this emission coming out of a black hole, exactly how much energy is coming out? I mean, these AGN are extremely energetic if we're emitting ultraviolet and optical and infrared, but ultraviolet, X-ray, gamma rays, all these very energetic photons. What is that really doing to the surrounding neighborhood? And so I tried to come up with like some sort of calculation to kind of quantify again with our human brains how much energy comes out of a typical supermassive black hole or a typical, active galactic nucleus. And so I did a calculation just for a nearby one. And so if we imagined that every grain of sand on Earth was an atomic bomb and we set them off at the same time, that's not enough energy to recreate the energy coming out of this nearby active galactic nucleus. What we need to do is clone Earth 160,000 times, take all of their grains of sand and turn them into atomic bombs, and then we detonate them at the same time. And that's how much energy you're getting out of a active galactic nucleus per second. It's crazy how much energy is coming out of these things. You can barely fathom how much energy is coming out of these supermassive black holes. So what does this energy do? I mean, it goes out there and it's running into the rest of that host galaxy probably. But I mean, what kind of effects does that have on the galaxy that these live in? So what I like to look at is ionized gas. And so here's a picture from, the TV show Chernobyl. Spoiler alert, there's a nuclear reactor that explodes. And so what they see in this picture, all these folks on this bridge are looking at radiation coming from the broken reactor, flooding above it, and it's ionizing, it's frying the air molecules that are above the reactor. And I think that they made it blue. I don't know if it was necessarily blue, but I think it was blue because that's the color of nitrogen. When you ionize nitrogen, you see predominantly blue, and that's the most abundant element in the atmosphere. So you see this blue light. So you have this source of very energetic particles that's running out into gas, air, and it's stripping electrons off of that gas in what we call ionization. So that same process is what we see happening in AGN. All right, so here's an AGN NGC 7582. And we can look at some observations that we typically take of AGN these days. And this is using an integral field unit. So what you do is essentially you take a picture of the galaxy that you're interested in, and at every individual pixel, you get a spectrum. And from that spectrum, you can figure out how the gas inside this galaxy is moving. So we can see that the ionized gas then here is kind of creating, this biconical structure, this flashlight of doom almost. And so the radiation is flooding out from above and below that supermassive black hole, and it's running into the host material there, and it's frying it in this kind of like biconical structure here. And so we can see the illumination of the massively powerful radiation coming from this supermassive black hole. And so we can map where the gas is, but we can also, oh gosh. All right, we're going to talk about the Doppler effect real quick. Sorry, I forgot that I had these in here. So the Doppler effect, I mean, if you're not familiar with what that means, is that we have sound or light coming from an object. And if it's not moving, we assume that the sound and or light that is in front of it is going to be the same frequency for sound as it is behind it. However, if we have this ambulance moving towards somebody, they're going to be receiving a higher frequency sound than the folks that the ambulance is moving away from. So the same thing then happens for light. So we use light and we know what color the light should be from an emission line, an ionized gas emission line. And so if it wasn't moving, everybody would be observing the color of this emission line to be the same. However, if that gas is traveling toward or away from us, we're going to have the wavelength of that photon change and be stretched out or compressed due to the Doppler effect. So if the gas is traveling toward us, it's going to have a shorter wavelength that's going to appear slightly bluer. And if it's traveling away from us, the wavelength stretches out and it's going to appear slightly redder. Does it mean that it's literally blue or red? No, it just means that the wavelength is just going to be a little bit shorter or a little bit longer. And we use the terms bluer or redder to talk about the extent of these wavelengths sizes. So coming back to our data here then, if we take our picture and we get a spectrum on each individual pixel and we measure the Doppler shift of each of the emission lines we're looking at, we can see that most of the gas in this galaxy is in rotation. So you have that big disk, and we can see that on the lower right-hand corner, it's rotating toward us, it's blue shifted, and on the upper left-hand corner, it's red shifted, it's rotating away from us. So most of the gas, this is probably an H-alpha map, is in rotation. However, if we look at the ionized gas, this is oxygen 3, it's ionized twice. We can see that, the ionized gas here is not doing rotation at all, but it's actually traveling radially, which means going away from the radius in a straight line, blue shifted toward us above to the upper right, and then red shifted down and away from us. So it's driven away from us to the lower left and driven toward us in the upper right. And so what's kind of happening here is the gas is being driven out of the plane of the galaxy, and it's kind of creating that splash along the hard, more dense material, not hard, but more dense material of the galaxy. So if you can imagine like the little mermaid when Ariel's on the rock and she's singing and that splash comes up behind her and the water is creating like that splash effect, that's the same thing that's happening then with this gas. The gas is being driven into and up along the dense parts of the galaxy and creating that splash effect that we're seeing here. So this gas then that we're seeing traveling, the Doppler shift is traveling very fast. The slower outflow velocities that we look at are around 300 kilometers per second. Again, doesn't make sense to me. That's around 600,000 miles an hour. What that really means is that you could drive on the highway from Seattle to Miami, expecting no traffic, and get to Miami in 17.7 seconds, or about the time it takes for that animation to complete. So that's how fast this gas is traveling on a at a low energy day. Sometimes it's traveling an order of magnitude faster than that. So what I want to kind of come up with this idea then is that these AGN create these beautiful structures that we look at that are so gorgeous with their lit up light. And we're like, wow, nature's amazing. It's so gorgeous out there. But if you're living in it, you're having a horrible time. There's winds that are traveling hundreds of thousands of miles per hour, and you're frying, you're getting you're getting radiation damage, and you're having a horrible time. So it's crazy how we, as astronomers, look at these objects from far away and think, oh, space is so beautiful. But if you're in it, you're just having the worst day, the worst. So the next question then, talking about AGN, is how do AGN affect their galaxies, right? We know they're bad, but we're still trying to really figure out the impact of these AGN on their galaxies. So what we know is that stars form from dense hydrogen gas in nebulae. So here's a picture of the Orion Nebula. Here's a little arrow because it's showing us how we're flying through a animation of the Orion Nebula then, and you had all these dense gas clouds that were able to cool and condense on each other, and eventually there was enough dense material to start fusing the hydrogen together to form stars, and that's how star clusters are formed. So for stars to form, you need cool hydrogen gas to just be chill and hanging out and condensing enough to form stars. And so what we think is happening is that AGN affects how that gas is allowed to form stars. So we think that AGN have what's called a feedback process that shows two forms of feedback. The first form is a preventative form of star formation, a negative feedback scenario. So I have a cartoon here on the right then that I thought made sense comparing to what's going on in these active galaxies, where you turn on the faucet and the water is hitting the sink and the water goes out everywhere out to a certain distance. And so at the small radii here, you're able to effectively drive material away from the center, and you're removing water or star-forming gas at these smaller radii. At larger radii, you're no longer able to remove gas and or water in this analogy, and it starts to actually pile up here. And so when you're doing that, what you potentially could be doing is pushing the gas together and promoting star formation. And so this would be a positive feedback scenario where we're promoting star formation instead of removing the ability to form stars. So there's two different forms of feedback that we're trying to understand that are due to AGN, and just how important each of these processes are to galaxies as they evolve over time. So feedback processes are observed at many wavelengths. So I'm used to observing in the optical and in the infrared and also in the radio, but you can see it in the X-ray. And so here's this feedback process that we just looked at in Markarian 573, that one I just showed next to the sink. And we can split up different emission coming from that source into different wavebands. And each of those wavebands potentially tell us a little bit of a different story that we can put together to come up with an understanding of what's happening in this galaxy. And then if we can apply that story to other galaxies and start stringing it all together to come up with a cohesive understanding of how AGN feedback works. So what we're going to talk about now moving forward is a little bit about this radio in the middle here, the radio emission. So a curious thing that astronomers have understood is that AGN ionized gas is often aligned with the radio structure that we see in AGN. So here's a couple different AGN, and we're going to actually go on a train ride here. We're going to look at a bunch of different AGN that are either imaging or the IFU data. The colors are the ionized gas and the contours are the radio structures. And these are publications by all sorts of people that show the radio contours, the radio emission, the contours are often aligned with the bright ionized gas structures. However, when we think about radio structures in like jets, radio jets, these are in AGN, these are in these very rare number of AGN that are very powerful radio structures. And so that's how we were originally introduced to radio signals coming out of active galaxies. And so when we look at these more plentiful aligned sources where the ionized and the radio structure are aligned, are we seeing similar processes that produce the observed radio sources? So this is a project that I did a couple years ago when I was working with the Naval Observatory, where we tried to start up this fundamental reference AGN monitoring experiment, or FRAMEX. And what we did here is try to understand the position of the nuclear X-ray and radio structures for 25 nearby very bright AGN. And so we had the observations in X-ray, but we needed to get the radio observations using the Very Long Baseline Array, which is a series of radio telescopes that range from Hawaii to the Virgin Islands, to get very high resolution radio imaging. And so we had to come up with a way to get the exposure times for the VLBA observations. So we used this thing called the fundamental plane, which was found originally by Merloni et al. 2003, which shows that there's a relationship between the radio luminosity and on the y-axis and the X-ray luminosity plus the mass of the supermassive black hole on the x-axis. This is an empirical formula. I mean, there wasn't necessarily an understanding of why this relationship existed. They just found that it worked out pretty well to use as a tool. So we used the VLA fluxes. We used fluxes from a different radio observatory, the VLA, to kind of guesstimate what we would be seeing with the VLBA using this fundamental plane. So, however, when we tried to get detections then using the VLBA, the fluxes dropped off or didn't even show up for a majority of our sample. And so we weren't really sure what was going on in this with this problem. Did our observations mess up? Did we screw up somehow? And so what we found was that targets with extended radio sources in the VLA, so the VLA observations are kind of a lower resolution, bigger structure imaging observatory. And we saw that objects with larger or more extended VLA flux had a bigger discrepancy between their VLA and the VLBA peak nuclear fluxes. And I realized I didn't share this 2021 paper with Kat and Vivian, so I'll share that with them for you guys to take a look at later. But what we think is happening then is that the radio structures are likely coming from an interaction between, or that there's more interaction around the nucleus for these extended structures than there are for the ones that are compact. And here's an example that, like, for NGC 1068, this one spectacular AGN, like the brightest peak is not even looking at the AGN from the VLA observations. So this fundamental plane using VLA observations might be a red herring for folks. And so we just wanted to make people aware of that. And then we were trying to understand if this relationship then between the flux differences between VLA and VLBA would be because it's due to a jet orientation effect. However, we see that if this was a jet, we would expect the peak measurements between VLA and VLBA to be large for pole-on orientations. And then if we were looking at the nucleus, then in an edge-on orientation, we would expect the difference between VLA and VLBA to be much smaller. And we found that our observations show the inverse of this relationship. So what this probably means is that what we're seeing then is this extended radio structure is always located in the host galaxy then, if it's always aligned with the O3 gas that we looked at from the imaging before. And this goes against what we're used to in these radio loud AGN, because these radio jets and these radio loud sources aren't related to their host disks at all. They shoot off into space and aren't running into gas lanes or any sort of optical ionized gas structures at all. So we're seeing a different sort of creature then going on for the majority of these radio structures versus these very beautiful large radio jets. And so what we're positing then is that the radio structure that we're seeing in a majority of these AGN is actually not due to a jet, but it's more due to it's a shock, which is a feedback process when something launched at high velocity, be it a wind or some maybe a jet that we're not seeing, runs into a material that is static. It's not really moving, like a thick dust lane, and that slamming into it creates this shock of energy, and that produces a radio bubble around it, very similar to what we see in supernovae remnants. So this is like 3 different pictures of supernovae remnants below, and so we think what we're seeing is a very similar process. And so to test this, I just compared what we know for jets in active galaxies. This is a known jet that's traveling. There's radio structure here traveling several times the speed of light. And so if we were able to look at that for a nearby galaxy that isn't radio loud, this is at 1068 again. We're able to measure the positions of the radionauts here, and we see that the difference in position over time is actually much smaller than the speed of light. We compared the position of these radionauts over 20 years, and we're seeing that the velocity that would be produced if they were actually traveling are less than 10% of the speed of light. And the 10% is the threshold that you need to create the relativistic state, because that's where you start including your gamma in your physics equations. So anything under 10% the speed of light is moving non-relativistically. So we're seeing that these things aren't acting like the jets that we're more familiar with in radio structures. And we can then see that this radio structure is also aligned with the dense molecular gas material in the host galaxy as well. So this is creating this idea then that the radio is just another byproduct of the material that's in the AGN, surrounding the AGN. So we're going to try to look at it in multiple dimensions here. The pink is cold molecular gas that is observed in the radio from ALMA. And from there, we can compare that to the hot, fried ionized gas of O3 in the green. And we can see that the green is actually like a carved out region that's creating this canyon through this donut of the molecular gas. And then we can see that the radio structure is along the surface then of part of that ionized gas, because that's where the winds are running into this dense material and creating the shocks here. So the comparison of the molecular, the ionized, and the radio structure is showing us that these are all intertwined. This is all material in the host galaxy. And that what we're seeing is just a very extended process similar to supernovae remnants going on in the host galaxy. So this is a new idea. It's not necessarily a totally accepted idea yet, because people are very comfortable with saying that the radio structures, no matter where they are or what they're doing, any radio structure that you're seeing is coming from a jet. So we're working on coming up with tests or redefinitions of terminology to help make it, I don't know, easier to digest that this is potentially not a relativistic jet launching through the host material, and is instead a product of AGN feedback. And so if we understand that it's part of this feedback process, it creates this really cool panchromatic atlas of feedback. So we start from the cold gas reservoir, we get to the warm molecular gas, and then there's low ionization state, and then the high ionization state, and then the X-ray, and then the radio is at the very end of it. So you kind of have this reservoir where radiation drives gas out of, and then eventually at the end, it reaches some point that it can't travel any further, and it imparts a bunch of mechanical energy to create this shock effect that we're seeing in the radio. So what are we leaving with here then? So the important idea then is that the radio structure that we're seeing in a lot of these AGN are not jets, but instead are this byproduct, this shock that's going on, that is where AGN feedback of some sort is running into the host material of the galaxy and producing this shock. And that's valuable because then, even though it's radio emission, it kind of gives us X-ray vision, in the sense that if we turn off all the rest of the emission coming from this galaxy, we can see that this galaxy has some sort of feedback process where the winds or the AGN feedback is running into the host material and shocking it. And potentially, when you're shocking it, you're compressing the gas and producing that positive feedback. So if we use this radio structure to understand that there is positive feedback happening in AGN, we can understand A, how often AGN are running into their host galaxies, and B, how much gas is being compressed in these galaxies to help people create more accurate models of survey level amounts of simulations. And then finally, are we in danger? So just it's the question that we often get is like, are we gonna be okay if the black hole at the Milky Way turns into an AGN? And so yes, I mean, there was an active galactic nuclei event about 2.6 or something million years ago. But we saw that the evidence of this active period are these high energy bubbles that are traveling perpendicularly to the plane of the host galaxies. We call these Fermi bubbles. So what that really means then is if there was ever another active galactic event, the line of fire is out of the plane of the galaxy, and that we'd probably be okay. We'd probably be pretty safe. So, right. With that, I can take some questions. Thank you so much. Thank you very much.
Thank you so much. That was incredible. Thank you. And I like that you added in there, we'll probably be okay. No, we'll definitely be okay.
Any astronomer worth their salt will never give you absolutes. Never.
Oh, yeah.
I mean, nobody's going to come back for you on that one. But good point. What a great presentation. We got so many kudos along the way, like great analogies. I love the animations. Thank you.
All
Thank
right.
you.
So
Thank you guys so much.
absolutely. So we do have some questions in the chat here. All right. So one of our questions is, so our bigger worry about black holes is not getting spaghettified, but it would, be that we would be toasted by radiation long before we got near the thing. Is that correct?
For the supermassive black hole, yes. I mean, that we're never going to be like falling into that. We're more than halfway outside of the radius of the. I'm sorry, like we're like the outer half of the radius in the Milky Way. So we're never going to fall into Sagittarius A star. However, yeah, there was like the worry that is there enough radiation that could like fry us potentially, but we're out of the line of fire, so we'll be okay.
Excellent, thank you. And then just to confirm, how do you get the X-rays and gamma rays from the accretion disk? Is it, the synchrotron radiation or nuclear reactions?
So this is a bunch of material that's swirling around, traveling really quickly around the supermassive black hole, and it's all rubbing together. And so that forms this gigantic thermal component of X-rays and ultraviolet rays and gamma rays. I don't really understand gamma rays because we don't collect them very often from AGN. It's hard to understand where gamma rays come from. So I don't know too much about gamma rays, but we do know that tons of hard X-rays and ultraviolet rays come from that center around that accretion disk. And so the synchrotron radiation I was discussing is a radio byproduct where you have some sort of collision that has freed electrons from, and so if you have this shock, you're ionizing that material and you've kicked electrons off of those atoms, and those atoms travel along the magnetic field line, and that creates this radio, the synchrotron emission. So you have to have free electrons and you have to have a magnetic field for them to travel along to create that synchrotron radiation. And typically that happens at larger radii, but we do see a little bit around the nucleus as well.
Great. So Hawking radiation says black holes dissipate their energy. So how does that affect AGN structures?
I don't know. Hawking radiation is a fun idea about matter antimatter creation, right? So like spontaneously you have like an electron and a positron form and then recombine and obliterate each other, and then nothing happened. But however, if like it forms near the edge of a black hole, then the black hole like accepts eats one of them, and the other one never recombines, and it then theoretically or literally the black hole has emitted a particle by that sense, and so then it has lost it. But I mean, I don't think there's no measurement that we've had that's like, oh, this black hole is looking a little skinnier this week than last week. So yeah, we haven't measured any sort of significant effects that would be due to Hawking radiation.
Okay. And since we just touched on it a little bit, can you say a little bit more about the formation of supermassive black holes?
Nope, because we don't know how they got there.
Fair enough.
There was some new results for an AGN out at a redshift of 10, which is near the beginning of the universe, and they measured the black hole mass to be half the mass of the entire galaxy that it lives in. If that's correct, who knows if that's correct. But if it's real, then that's a really big question mark about how was a supermassive black hole able to get so massive even at such an early time. So we don't understand how they got there. That's a big question mark about the origins of the universe and black holes.
And so we did have a question in the chat here. What is the possibility that Milky Way Sagittarius A star could turn into an AGN?
Not good. So I mean, there was this, excuse me, there was this exciting little time, probably like a decade ago, where there was a high velocity gas cloud that was kind of traveling near the near Sagittarius A star, and we thought it was gonna maybe go too close and kind of be eaten and accreted, and there would have been like a little flash, and we'd be like, ooh, it'd be so exciting to see what happens to Sagittarius A star. But then that gas cloud just whipped by and didn't go in, and they're like, oh, okay, what do we do now? So, yes, there's usually you need some reason for the gas to stop orbiting around the black hole and fall in. So like if we like astronauts orbit around the Earth and are going to keep falling past the Earth unless they lose their angular momentum. So if we built up a giant wall and the astronaut ran into that wall, they'd lose it and then they'd fall to Earth. So there has to be like a collision that robs energy, this momentum of stuff to have it fall into the center. So we don't have anything like that likely happening anytime soon.
Okay. And then we did have just one clarification ask in the chat is, could you define fundamental plane in this context?
Right. So this fundamental plane, a plane just means that it takes three different variables to form that relationship. So it's a relationship between the radioluminosity and the X-ray luminosity and black hole mass. So there's two variables here and there's one variable here. And they said, well, if we take those three variables and we add some cocktail of their like 0.6 of this and 0.7 of that and 0.25 of this, that creates this relationship. And so that's neat. And what does that tell us? We're not really sure, but you could potentially use it if you knew the X-ray luminosity and you knew the black hole mass, what you could expect the radioluminosity to be then. However, we found out that that didn't work out using different observatories, a higher resolution observatory for the radio. So that's where that fundamental plane then fell apart.
Okay. And then we have another question. So what are some future studies which we could all follow up on this?
Right. So I would like to, I mean, what could we do? So there's a really cool survey called VLAS. VLAS is the Very Large Array All Sky Survey. And so it is then I think probably like it's like 3 gigahertz or something like that, where it's the VLA, which is a radio observatory, has observed all of the sky. And what I would like to do eventually is look at where all the AGN are and measure how extended the radio structures are for those AGN. So if you can measure like the extent of them and see if they weren't circular or if they were circular, like if they were a point source, if they were extended, and do like a census of like the morphologies of radio structure for nearby AGN. Under the guise that that is a feedback process where the AGN is like the feedback is running into the host galaxy, you then have a census of how often AGN are running into their host galaxies. So that is something we could be doing. Otherwise, I also think in the infrared is very interesting. In the near infrared, looking at iron 2. So iron 2 is like 1.2 microns. And that is also a shock diagnostic. So you can use that to measure how bright shocks are in these AGN. And so if there's any sort of significance with the ionized gas in the optical versus this shocked emission line signature, there could be something to learn there as well. So catalogs of iron 2 and radio morphologies are something that would be very helpful for the community.
And then there was one more question. Everyone wanted to know, is there a way that we could access these slides to use in presentations now?
You can invite me to come talk somewhere else. I'm always around. So
Hey,
happy to come chat some more.
like the sound of that. So we had a question about the Euclid telescope. Would the Euclid telescope find more AGNs?
So the Euclid telescope is a survey telescope, but I don't know. Probably, maybe. I don't know. I don't know. I should know more about Euclid because I'm an ESA or astronomer. I'm part of ESA, so that's the European Space Agency, and so I should really understand more about what Euclid does for my research individually. But I believe that it's more of a survey instrument, and I'm more of a deep dive into a single object person. So I don't try to think about what Euclid could be doing for me, but I should. I don't
We
know if
won't
it's
tell anyone.
or AGN though necessarily. I think it's an optical and might be difficult in the optical.
Gotcha. Well, we won't tell anyone. That'll stay between friends.
Yeah, this is not going live anywhere, or it's not being saved forever.
Definitely not. All right. Let's see if there are any more questions. Vivian, do you have any other questions that you want to pull from the chat here?
Yeah, there was a question about recently in the news, there was a report that a very massive supernova explosion resulted in thinning the ozone layer in the Earth's atmosphere temporarily. The report said it occurring 1.9 billion light years away, and she was amazed. She thought that we wouldn't have to worry about it if it wasn't within about 20 light years of Earth. But now they say it could threaten our environment from that far away. Do you?
And I want this article. Let's circulate this article. Let's take a look.
Let's find it. If anyone knows what Linda is talking about, please, or if Linda, you know where you saw that, just throw it in the chat. And let's see if we can figure it out.
Supernova explosion. Okay. So it's not going to be 1.9 billion light years away. I mean, we look at the galaxies that I look at are mega light years away. So and the only supernovae we'd have to worry about are supernovae in our own galaxy, and that's like thousands of light years tops. So the 1.9 billion will probably okay. Probably like what was that? I don't know. Oh, there's another one. I don't know. Yeah, it's probably okay. But yeah. Here's Kat, is this the article?
The article.
Supernova explosions.
I believe so.
Gosh. All right. I'm not going to weigh in too much on this though, because it's a supernova explosion and I'm not an expert, but so this is they happened a long time ago and maybe had repercussions on the environment back in the day. And so I think that's what they were seeing.
Okay, I found one from
the Earth atmosphere was changed during the Ice Age. And then okay, so yeah, totally plausible. I thought, yeah, I mean, who knows what happened back in the Ice Age and earlier eras. So I feel like that's very feasible if they have evidence for that. I thought it was like something that happened recently or something. And so, yes, I mean, there are concerns, I think, of like Betelgeuse going supernova and exploding and how beautiful that would be. But then it's like, are we gonna be okay if that happens? I don't know. Like, that could be a problem. So very similar to those folks looking at the Chernobyl explosion, being like, wow, so beautiful. So like the radiation's killing them. So yeah, I'm not sure about the supernova explosions. I'll read more of that article. Thank you for sharing.
Yeah. There was a supernova. Oh, here we go. Found it on NASA. There we have it. Try this guy. That's the one, I think. And it was just recently on the October of this year. Oh, no, sorry.
How radio? Yeah, so this is a gamma ray burst.
Wow.
Again, I'll have to read it. I mean, we're just gonna sit here silently, like scrolling.
Sure. Sorry.
It's not interesting stuff. So, but I mean, this is interesting. I'll be sure to read it, but it's not interesting to watch people read an article.
Cool, Linda. I didn't see that one. That's really cool. Lawrence was asking if you're going to get time on the 39 meter. Do you have any idea?
What is the 39 meters? Is that the ELT, the extremely large telescope or something? Or
39. I don't know which one that one is.
9-meter telescope. 39-meter telescope.
The extremely large telescope.
So the ELT. Who knows? I mean, ELT is when's the projected time for this thing? First light. I don't know. First light's not going to be let's see, first.
All right.
But first light is planned for 2028. So I got some time. You got to think about some programs, some proposals for it. Typically, you got like a proposing period, maybe a year out or something that you can submit for. But right now, I have I have as much time as anybody else on Earth with the ELT. So,
Fantastic.
All right. Well, thank you so much, Dr. Fischer, for spending your time with us here at Night Sky Network. For our Zoom attendees, a survey link was posted in the chat. Vivian, if you could post that again, just because we've had some links dropped in since then. And, we always welcome your feedback, your comments, your suggestions, questions, concerns. And you can find this webinar and past webinars on the Night Sky Network YouTube channel. If you just put in NASA Night Sky Network into the search, it'll come right up. And if you are interested in this and more, tune in next month on Tuesday, December 19th, where we'll hear from Dr. Robert Nemiroff for the Astronomy Picture of the Day 2023 year review. That's always a favorite of ours here at Night Sky Network. Keep looking up, and we thank you so much for tuning in tonight.
thanks, everybody.
Sure. What a treat. See you next month.